Hi everyone, I'm going to go ahead and go through all these questions that were on homework 26. I'm going to help you set it up. I'm not going to solve it, but I'm going to help you set it up because I know that could be slightly confusing, especially when it comes to these types of optimization questions where there's actually a situation. So the first question, find the smallest perimeter and dimensions for a rectangle with the area of 36 inches squared. So a couple of things I'm thinking is that, okay, we know perimeter is x for a rectangle. Let's draw a rectangle. Sometimes I like drawing them out. So here's a rectangle, and we'll call this x and y. And the perimeter is x and y and y, right? These are just the lengths of the sides. So it's 2x plus 2y equals to some type of perimeter, all right? Some type of value. And then we said the dimensions of the rectangle with the area. So they'll give you two conditions. One you want to optimize and one you want to set up. So the second part is, what's area? Area is equal to x times y equals to 36. So we're trying to optimize this guy because we want to minimize this, but we have x and y and we don't want to deal with those two variables. So we're going to use the second equation, steal one of the variables and plug it in as a replacement. So in this case, I'm going to say, we'll solve for y. Y is equal to 36 over x. And then I'm going to replug it back into here. We're going to say 2x plus 2 times 36 over x equals, I'm just right here, no, equals to, turn it around space, equals to p. And now we can solve for p prime, which is our derivative, and we're going to go ahead and take the derivative of this guy, which would have been 2 plus, okay, this is 72 over x, being rewritten as, I'm running out of space here, let's jump over here, 72 over x to negative 1, that's the same idea. The derivative y prime, y prime of this, the derivative of this is negative 72 over x squared. So let's write that. So we negative 72 x squared. Let me erase this. It becomes a negative 72 over x squared because we took the derivative. And we're going to make that equal to 0 to look for its critical points. So the question is here, find the smallest perimeter of the rectangle of the area. So we have an equation we want to optimize, and that's the equation we're going to take the derivative. But I don't want to take the derivative with three variables, x, y, and p. So I'm going to use the second equation to get rid of one of the variables. You can swap x or y out, and we only have to find p prime, which is automatically going to be the derivative of p. And then we're going to take the derivative of x, which gives us this nice value here. Now, to make this go to 0, we're going to go ahead and simplify it, common denominator. So it's 2x squared minus 72 all over x squared. So we know the 0 doesn't exist at 0 when x is 0, and we didn't think that was going to be max anyways. And the top is going to be 0, so I'm running out of space, I'm sorry. We're going to say 20, 2x squared minus 72. When will this equal to 0? X squared equals to 36 because we add 72 divided by 2 is 36, and x equals to plus and minus 6. We cannot be a negative 6, so it's going to be a 6. So we know x is 0 at 6, and so I'm running out of space. I'm going to draw my sign chart here. At 6, we know we have a derivative of prime, a critical point at 6. Let's make sure this is a minimum. So let's plug in a number on the left and the right side of that critical point. So if I plug in a 5 here, if I plug in a 5 here, we see that that's going to be less than 72. So we know we're going to have a negative. And if I plug in a number bigger than 6, like 7, 8, 9, 10, that's going to be bigger than 72 as a plus. So this is a minimum value at 6. Now, the problem is, now that we found where the minimum happens, what would the minimum be? We would have to plug in this part here. If x is 6, then y is 6. Now we can plug in 6 and 6 here, and we have a minimum value of 2 times 6 plus 2 times 6 is 24. And that would be our minimum perimeter. Because we're trying to solve for the perimeter, right? And if x is our minimum, our y value has to be 6 to get to 36. So we have our x and y. Darn it. So I ended up actually solving that question. So all our problems end up that way. We have a problem we want to optimize, And if you have too many variables, there better be another equation there where I can substitute it so we don't have so many variables. And then we take the derivative to find the prime value, set that equal to 0. So let's look at the next one. A rectangle is constructed with a base of x, based on the x-axis, so something x-axis, and its upper two vertices on the parabola y is equal to 64 minus x squared. So we have some graph, and the graph looks probably something like this. We have 64 is up here, and a negative parabola coming down, and we have a rectangle that's formed inside this. Okay, that's our rectangle inside of it. What is the largest area the rectangle can have, and what are the dimensions? Okay, so we have to optimize our area equation. So let's write an area equation. A is equal to base times height, right? The base here is our x value, right? That's an x value, but times 2. So we're going to say that's 2x, and our height is our y value, which is the equation. Y is equal to 64 minus x squared. That's our area equation. So we have to be very creative on how we create our equations. But does this fit? Let me ask you, to find the area, that's our base times height, right? So the base would be, if I call this x, that's x, and x, that's to be 2x in length, and the height would just be the y value. So how do you get good at this? You just keep practicing the same questions over and over. Just like how to get good at Spelling Wednesday. You just keep doing it. Okay, now that we have our equation we want to optimize, because let's read this again. What is the largest area? So we're going to optimize this. We're going to find a prime. And in this equation we only have one variable because we plugged in our height to this. And we're just going to go ahead and take the derivative of this. You can multiply it out first, or you can do product rule. It's up to you. Okay. Now, once we find optimizing our critical points, we can check if that's a min or max. And then we could then plug in, find our values of what they want. Let's go ahead and set up the next one. Find the dimensions of an open rectangular box of the maximum volume it can be made from a sheet of cardboard 23 inches by 13 inches by cutting congruent squares from the corners and folding the sides up to find the volume. Okay, we're going to have an open box. So an open box looks something like this. Whoops, that looks terrible. I'm sorry. I don't know why I drew them crooked. We should draw straight. These are crooked. Okay. And this opens up flat, and we're going to look at a rectangle, something like this. And we're going to cut off squares from the corners. And there are a couple of hints to this problem. One is that you're just going to write x in the corner, because we don't know what the length of those x's will be, but they are squares. And if you fold the corners up, you end up with a box. Okay. Now, find the dimensions of the open, So the cardboard is 23 inches long and 13 inches, this going this way. So then find the volume. Now what's the volume equation? The volume is equal to length times width times height. So these are the three aspects that we have to make sure we multiply by. And we're going to find those values coming from this box over here. So the volume would be our length going this way. Wouldn't it be the whole 23? It would be 23 minus 2x, because we're going to subtract those, cut out those corners from the edges. Our width would be going this way, 13. So 13 minus 2x. And our height would be this length here, right? That length, and that is the length of x. So we have our volume equation. We want to maximize it, so we're going to find v prime. So in this case, I would probably multiply first and then take the derivative. That would probably be the fastest. And then we can figure out how many different options we have to as critical points, and which of those would be a maximum value, not a minimum, a maximum. 4. A rectangular plot of land would be bound by a side of a river. Very popular question, the side of a river. Hi, river. That's a river. I'm going to draw that with blue if I want. Here's my river. And then on the three sides, we have a single strand of electrical fence. All right, great. That sounds nice for these animals. Here's my electrical fence. It's going to form a rectangle. And the length of the wire is 1,100 meters. Okay, so I'm going to label this as X, x and y. You can label however you want. You can say yxx, doesn't matter. I just started off with x. So we said 2x plus y would lead me to a maximum value of 1100 meters. Okay, so that is in a sense for the perimeter. We don't know what x and y. Now the next question, what is the largest area you can enclose? Well, area equation is length times width here. So area is x times y. And since we said the largest area, we're going to maximize this area equation. Now, I could say a prime right away, but if I did that, I would have to deal with two variables when we don't want to. So let's get rid of the x or y's. I think y would be easier here. So y is equal to 1100 minus 2x. We plug that y in. X, parentheses 110 minus 2x. I lost a 0 there. Minus 2x. And now we can see it's really just not that hard of a question now. It's 1100x minus 2x squared. And then I could optimize this by taking the derivative. So find what a prime is and set that equal to 0. Those are the critical points, and we can then test using our sign chart if it's a maximum or minimum at those values. If I have more than one, in this case we only have one. Number 5, a rectangular tank that is 864 feet cubed with so that's a volume, right? That's a cubed is volume. And a square base that and an open top to be constructed of steel sheet that's a given thickness. Find the dimensions of the tank with a minimum weight. Okay, so we want to use as least material as possible to end up with this volume here. So the volume, let me just draw this real quick so we can see this again. Sometimes it's nice to draw so you can visualize it. So the base, or length times width times height, length times width times height gave me the volume 864, and then that's feet cubed. Okay, we're going to change those to variables that we can use. Okay. With a square base. The great thing they told us it's a square base. That was a hint I didn't catch. So if I call this L, we can call it L over here. So it's L times H equals to 8, or L squared, 64 feet cubed. What else can we glean off this? We want to minimize the weight. So to minimize the weight, we need to minimize the amount of area we use, the amount of material we use. So we said we start off with a sheet. A rectangular tank has a square base and open top to be constructed of a stained sheet of a given thickness. Find the dimensions of the tank with a minimum weight. So let's see, what am I trying to optimize here? If I optimize the weight, I guess that might be the amount of area I use. Constructed of a steel sheet of a given thickness. Find the dimensions of the minimum weight. So let's maybe think, if this is opened up, so we want to minimize the area that we would use. So the area of this, we say call this x and x, right? Because that's the square, and we'll call the height the y. Let's add up all the parts. So I'm thinking maybe it's area of all the parts. So maybe it's, how many wings do we have here? We have all these 4 flaps, 1, 2, 3, 4. Let me highlight those. 1, 2, 3, 4 are all the same size. That's 4 times x times y. Plus, we have the square, would be x squared. And that would be my area of material that I would use. And we're going to minimize this. So I'm going to say a prime. Take the derivative of that. But we don't want 2 variables, so I'm going to steal a variable here. Back here, we can say x squared times y is equal to 864. I'm going to move this around. Y is equal to 864 over x squared. Sorry, that's x squared on the bottom, okay? X squared. Now y here, I'm going to go ahead and substitute that, is going to be 4 times 864 over x squared and we had x there already, plus x squared. We're going to simplify that out to become 4 times 864 over x plus x squared. Then we're going to take the derivative of that and plug in 0, and that will tell us our critical points that we can solve there. This was a little tough one. I had to be a little more creative here. Okay, for this next problem, Johnny is designing a rectangular poster containing 36 inches of printing with a 3-inch margin at the top and bottom and 3-inch margins on each side. What is the overall dimension that will minimize the amount of paper used? Okay, we are given a poster. The area is equal to 36 inches squared. Okay, so let's use this here since it's here. So we have a x and a y value. Just to start off, we have margins on each side. They're 3-inch from the top and bottom and 3-inch on each side. So it's going to be, what is the minimum amount of paper used? So, Johnny is designing a rectangular poster contains 36 inches of print. Oh, within a margin. Okay, so we have a poster within a poster. So this is the inside value, right? With 3 inches on each of the sides. So we have x plus 3 on both sides was x plus 6 times y plus 6 because there's 3 inches on top and bottom, and that will give us our area equation here. Okay. And what else can we say? The x times y equals to 36 because that's the dimensions of inside. We can go ahead and solve for our x value here. X equals to 36 over y, and we'll plug that in here. So we end up, my area is x plus 6. Again, this is the area of the full poster. Let me put F there. Full poster, and this area of the inside poster. Times, we said y is 36 over, wait, I substituted the wrong thing. Over here, we want y. Y is equal to 36 over x. 36 over x. Plus 6. Okay, and then we're going to take the derivative of this value. We can do product rule if you want. And then we're going to set that equal to 0. The two sides of a triangle, next one. So that's a setup. Again, it's all pretty much the same. Once you end up with your optimizing function, we take the derivative of that and we set that equal to 0 to look for our critical points. Two sides of a triangle are 14 and 15. Sure. Let's say 14 and 15. Find the length of the angle that's formed by the sides that will maximize the area. Oh my goodness. Maximize the area of the triangle. Two sides of a triangle are 14 and 15. And the side of the angle theta in radians formed by the sides will maximize. I see. So this angle here in the middle between them here's my angle between them. That's going to be theta. We'll maximize the area of this triangle. All right, so we have our setup here, and we want to maximize the area. Now, if you remember from pre-calc, we have an equation for this, I think, and it's 1/2 AB sine C, where A and B are the adjacent sides and C is the interior angle. So our area here is 1/2 AB sine C. Let's rewrite this as 1/2 14 times 15 times the sine of theta. And we're going to go ahead and maximize the area. So since we have our equation here, to maximize, we just take the derivative of this. So what's A prime? Taking the derivative of this problem. Okay. So it'll just be taking the derivative of this guy. And you can simplify 14, 15, divide by 2 first, and take the derivative of sine. It gives us cosine. We can make that equal to 0 and find out what value would work here. Again, no matter the situation, I'm still doing the same thing. I'm just trying to figure out which equation they want me to maximize. I come up with that equation. If there's too many variables, I look for another equation where I can fill in the gaps so I don't have to take the derivative of so many parts too many variables. What are the designs of a rectangular, circular cylindrical can whose manufacturer will take waste into account? There is no waste in cutting the aluminum for the sides, but the top and bottom of the radius r will be cut from squares with a measure of 4r units. So the squares that we're going to cut for the caps are 4r units on each side. So 4r and 4r, because the radius, right, would be 2r, right? Or it would be r and r. So 4r units on each side. The total amount of aluminum used by the can will therefore be A is equal to 32 r squared plus 2 pi r h, where h is the height of the right cylindrical can. Okay, so this is the 2 part, and this, I guess, is the 2 caps. Amount of aluminum used up by the can will be therefore the area is that, where h is the height of the, okay, what is the ratio of h to r for the most economical can? Oh my goodness. What is the ratio of h to r? What is the ratio of h to r? Ratio is h over r. So that's what they want us to set up. My goodness. Okay, so we have the volume is equal to pi r squared h. And we know the volume is 108 pi r squared h. So if we're going to take the derivative, let's take the derivative so we have the r at least. So I'm going to get rid of the h. So that's all for h. So it's 108 divided by pi r squared equals to h. And then we can come back and write our area formula because we're trying to optimize our area that we use. 32r squared plus 2 pi r, and then h is now 108 over pi r squared. We can simplify that to become 32r squared plus the pi's divide out, one of the r's divide out. So we're left with 216 over r. And then we can take the derivative of this and set that equal to 0. And that is the basic process. After we find out what r is, we can plug it back r here to find what h is, and then we can just write that ratio that they asked for. Okay, suppose the next problem is r is equal to 64 squared of x represents the revenue, and c is 2x squared represents the cost, and x measured in thousands of units. There is a production level that maximizes the profit. So what is it? So when it comes to profit, it's our revenue minus the cost, and that's our profit, right? Revenue is how much we're making from the product. C is the cost, how much it costs for each unit, and we subtract them, and that's our profit. So we want to maximize this. So we just write 64 square root of x minus 2x squared, and then we are going to set that equals to p, and define the optimization is we just take the derivative of that and make it equal to 0. P prime equals to 0. And then we can check if that's the maximum. Once we have that x value, the question is, yes, profit is maximized when the production level is at blank units, or there's no way of maximizing it. Maybe this was a losing venture from the beginning. Next value, suppose c equals to, let me erase this. Suppose c is equal to x cubed blah blah represents the cost, where x represents in thousands, is a production level that minimizes the average cost. So what is it? So what is the average cost? See, the thing is, they told us not just the cost, the average cost. So the equation for average cost is you take the cost and you divide it by the number of units. In this case, x is in thousands of units. So we're going to, so to minimize our, so our average, this is our average equation. So let's write it. X cubed minus 4x squared plus 40x. Divide this by x. Actually turned out to be an easy question. X squared minus 4x plus 40. And then we're just going to take the derivative. A prime and set this equal to 0. Determine the function that might be minimized. They told us the function that might be minimized is this divided by x, because that's the number of units. A right triangle whose hypothesis is, here's my right triangle, draw a right triangle, whose hypothesis is square root of 13 meters long, that revolves around one leg that is generated by rotating the circular cone, so I figure it's going this way. Find the radius, height, and volume of a cone with the greatest volume that can be made. So volume equals to 1/3 pi r squared h, because it's a cone. A right triangle whose hypotenuse is square root of 13 long revolves around the length of its leg to generate a right cone. Find the radius, height. So the idea is, I guess this could be shrinking or increasing, because it didn't tell us a height that can be made. So we're trying to find the greatest volume. Now we have a relationship between that's my radius and my height, and since that's a right triangle, we're trying to get rid of one of these variables. It's always trying to get rid of one of these variables, and I'm going to get rid of h, because since it is a right triangle, we can use Pythagorean Theorem, and we can say h is equal to, let's do h squared, start from scratch, h squared plus r squared equals to square root of 13. We're going to move it around. H is equal to square root of 13 minus r squared, and we take the square root of that. So our volume is equal to 1/3 pi r squared times the square root of the square root of 13 minus r squared. And then we would have to take the derivative of this, set equal to 0, and then we can maximize our volume based on whatever r they give us. Once you find the r, we can plug it back in here to find the h. So we have the height, and then we have the volume once we have both. This question is a little tougher. Number 14, what is the value of a and b that makes f of x equals to x cubed plus ax squared plus bx half? So a local maximum at -1 and local minimum at x equals to 5. So this is our solution that they want us to get to, right? So we have a local max. So here's what happens. It's our derivative has critical points, and we have a max at -1 and a minimum at 5. That means the slope has to change from a negative to positive to negative, because that's a max, and then back to a minimum. So we go negative to positive. Okay. So let's go ahead and take the derivative of what they have. F prime would be 3x squared plus 2ax plus b, and we want to make this equal to -1 and 5. So find the values of a and b given this function that have a local max at -1 and a local min at 5. Okay, so I took the derivative and I'm looking at the critical points. When does this equal to 0? So this is equal to 0. So 3x squared minus 2ax plus b. Okay, so what could we do? We could try, I feel like maybe we could try factoring this, because we have to have two zeros here, and the answers to our solutions have to be -1 and 5. So if is this factorable if I make up something? This is for sure 3x and x. And we're going to have, let's say this is 1 or b and 1. So our a value has to be somehow that combination of those numbers. And 3x b plus or minus 1x. Okay, we'll just call these plus and plus, and then the b can change. Has to equal to -2ax. There's probably a way of doing this, but let's just say one of these values is, if I make x, and what if I make b 1, be 3x plus 1 3x plus 1. No, that means that x is negative 1 over 3. That for sure is not right. So we have to think of a b value. 3x squared minus 2ax plus b equals to 0. And what could a and b equal to so that x is, well, let's make x 5 right now. 3 times 25 minus 10a plus b equals to 0. And then our next verse, oh yeah, this, so I get it now. So this is a system of equations, I think. Wait, is it? No. Yeah, okay, so let's say it's a system of equations. So we have 75 minus 10a plus b equals to 0. So this is negative 10a plus b equals to 75, negative 75. In our second version, if I plug in negative 1, so it would be 3 times negative 1 squared minus negative 1 times 2 is positive 2a plus b equals to 0. So we're left with 3 minus 2a. Is that right? No, that's a positive 2a, right? That's a plus 2a. And then plus b equals to 0. And we're going to rewrite that as 2a plus b equals to negative 3. We can try simplifying that. That's 8. Nope, we have to change one of the signs, I'm sorry. So if I make this positive, negative, positive, that's going to be 12a plus 2b, oh no, sorry, the b's cancel out, is equal to 7 positive, so 72, positive 72, a is equal to 6. If I know what a is, let's plug in a there. 3 plus 2 times 6 plus b is equal to 0. That's 12, 15. B is negative 15. Let's try that on the other side. 75 minus 10a minus 15 is equal to 0. And then that's 60 minus 10a equals to 0. A is equal to 6. Yep, okay, we found our a. A is 6, and then b is negative 15. Oh, that was a tough one. Then find a local minimum of negative 8 and the point of inflection at 2. Okay, I think that would be easier. The point of inflection is when we take the second derivative. So if we take the second derivative of this guy here, we end up with 6x minus 2a, make that equal to 0, okay? But we know it happens at x is equal to 2. So if x is equal to 2, that's 12 minus 2a equals to 0. So a must be 6. Okay, if a is 6 here, the b value, we can go back to our last equation, 3x squared minus 2a x plus b is equal to 0. And then we said we know that there's a local minimum at 8. So we just plug in the 8. 3 times 8 squared minus 12 times 8 plus b is equal to 0. And that'll be 64 times 3 is a huge number. 64 times 3 is 240. 64 times oops, not 64 times 3 is 180, 192 minus 96 plus b 0. That's going to be 80, no, 98, I think. 98 plus b is equal to 0. B is equal to negative 98, perhaps. Anyways, okay, so at least hopefully you get the idea. I think I'm out of time, so if you need more help, please let me know.